What we have here are two pendula. On the left we have a physical pendulum, which is a meter stick pivoted around the endpoint, and on the right we have a simple pendulum, which is a very light string attached to a very heavy mass. I'm showing the tops where the pivots are so that you can see that the simple pendulum is clamped a little bit above the physical pendulum, and that's because when I pan down, it will look like the simple pendulum, the ball on the string, is shorter than the meter stick, but they're actually the same length. And I want to show that because when I set them oscillating, one of them will oscillate faster than the other, and it's not because there's any difference in length. You should see that I started them at almost the same point in the swing, but then they get out of sync with each other because they have different periods. The physical pendulum of the meter stick oscillates faster than the simple pendulum of the ball on the string. We will derive equations for each of these guys, usable equations to describe the period and how it relates to the length of the pendulum. A simple pendulum is one in which the mass of the pendulum bob, as I just showed you, is considerably more than the string that is supporting it. All of the oscillating mass is concentrated at the end point. This is an approximation, and we can only do this when the mass at the end point is considerably more than the mass of the string. The physical pendulum is one in which the mass is spread out along the radial length from the pivot to the end point. And the result of that is that we have to account for that rotational inertia. For the simple pendulum, rotational inertia collapses down to the rotational inertia of a mass on the end of a massless ideal string. For this video, let's focus on the simple pendulum, and then if there's time at the end, I will go back to this and rederive the short version to get the period of a physical pendulum. So we're going to analyze this using Newton's second law for rotation, and we're going to have to make a couple of mathematical approximations along here in order to get this equation not to be absolutely awful. So let's start with Newton's second law for rotation, which is torque. Torque is going to cause that pendulum to swing back and forth. So here we have a diagram of the pendulum at its starting point when it has been pulled to the side. By an angle theta. Since it's been pulled to the side by an angle theta, and we're going to ignore friction and air resistance, and we're going to pretend that all of the mass is concentrated in the bob at the end of the string, and the string itself also has no mass. And this thing is going to swing back and forth indefinitely. Let's take a look at the forces on just the pendulum bob from gravity and from tension in the string. Gravity points straight down. And the tension in the string points along the string. Now this pendulum bob is going to swing back and forth in a circular arc, part of a circle, and it's going to be moving perpendicular to the tension in the string. So what we want to do, since its motion, its entire motion is perpendicular to the string, we need to split up the weight into components that are parallel to the string and perpendicular to the string. So parallel to the string and perpendicular to the string. And the piece of, for this motion, the piece of this weight that we care about is the part that is perpendicular to the string. The geometry that we're using here is what we have is two parallel lines, the vertical line up here and the vertical weight down there that are cut by a transverse. So the angle up here with the vertical is going to be the same as the angle here. And because of that, what we want is the sine function to find that side of the triangle. And this part of the weight, mg sine theta, is always going to point back towards equilibrium. Equilibrium is straight up and down. And when the pendulum bob is pulled to the right, mg sine theta will point to the left. If, however, I pulled it to the left, this triangle would get mirrored, and mg sine theta would point to the right, down and to the right. So that mg sine theta is going to create a torque on that pendulum bob, and that's what causes it to swing back and forth. So we're going to need a minus sign on this side here. When we zoom in on the torque, and the torque is going to be caused by the length of the string crossed with the part of the weight that is perpendicular to that length of the string. So remember, torque is R cross F, and it causes that pendulum bob to oscillate back and forth. The length from the pivot to where the force is applied, that's the length of the string. We already did the cross product in finding the part of the weight that is perpendicular to the string. That's mg sine theta. And then the last piece is it plus or minus? Well, since it always points back towards equilibrium, we need a minus sign here to indicate that it is always going to point back towards equilibrium. And that's the piece of this equation that makes this almost simple harmonic motion. It is not actually simple harmonic motion, as we'll see on the next board as we have to deal with that sine theta, but it is almost simple harmonic motion. So let's substitute what we know from our diagram into our equation here. So we're going to need a minus sign. R becomes L, and the cross F becomes mg sine theta. The next substitution that we can make is for the rotational inertia, I. We started out by saying that the simple pendulum is a massless ideal spring that has no friction at the pivot, and we're ignoring air resistance. So all the mass is just inside the pendulum bob. So a mass on the end of a string has a rotational inertia of mr squared. So mass on an ideal massless string and that's going to be mr squared, and in this case the radius of the circle that's going to be described by the motion is the length of the string. So I'll just skip straight to ml squared there. When we substitute those guys in, we're going to have minus mg L sine theta equals ml squared alpha. Now we have two things that we have to deal with. First, we have to deal with this sine theta here. And then we have to deal with the alpha. Because what we have here are two different variables, which is very awkward to have in one equation. So we have to find a way to get rid of the two different variables. And what's worse is one of those variables is inside the sine function. So we have to figure out a way to get rid of the sine function. So the way we're going to get rid of the sine function, let's do that first, is we're going to use the Taylor series approximation. The Taylor series approximation is a way of turning something that is not a polynomial into a polynomial. The sine is not a polynomial. So our function that we're trying to approximate here is sine theta. And the way we turn it into a polynomial is we use a series of derivatives. So we're going to use sine of 0, and then the first derivative of 0, and then the second derivative of 0. And so those are just numbers. So the Taylor series turns this guy into what is the value of this guy at 0 times our variable, in this case x is going to turn into theta, over which term is it, factorial. And our variable also has to be raised to the appropriate power. You should notice that this is the 0th derivative of the function. So it's the original function, plug in 0, what number do you get? And then here we have the first derivative and the first power and the first factorial. And then we have the second derivative and the second power and the second factorial and so on and so forth down the line as far as you want to take it. Now, if you take a look at this, we're going to be dividing by bigger and bigger numbers. So by the time you get down to the 9th factorial, dividing by 9 factorial makes that term very, very small. And so you're only going to want to take it down to the 9th term if you really need a lot of precision. Let's use sine 0 and its derivatives and see what the Taylor series approximation, that's what this is. Or if you want to take a look at the compact form in summation notation, what we have here is the compact form where we say we're going to add up from the 0th derivative to as far as we need this, and that's going to get us the value at where we want to be. Now I plugged in 0 for A here because I want it to be around the angle 0, also known as the vertical for us. But you can do this around any point on the sine curve. Sine of 0, so sine of 0 is 0, plus, well, the first derivative of sine is cosine, so this will become cosine of 0. Cosine of 0 is 1, and then we're going to have theta to the first over 1 factorial. Derivative of cosine is minus sine. So minus 0 theta squared over 2 factorial. Derivative of sine is cosine again, but now we're going to have a minus sign, so minus cosine 0. Well, that's going to be a minus 1. Theta cubed over 3 factorial. And we can take this further, but the pattern is just going to repeat. Because then we're going to be back to sine of 0, which is a 0, and then cosine of 0, which is a 1, and then minus sine of 0, which is a 0 again. And what you should notice here is that sine of 0, all of the sine terms disappear because we will be multiplying by 0. And the only thing that will survive is the cosine of 0 terms, where we're multiplying by 1. Second thing I want you to notice is it's the even terms that disappear, and it's the odd terms that survive. When we get rid of the terms that disappear because we're multiplying by 0, sine theta turns into theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. And the pattern will simply repeat with all of the odd powers, pluses and minuses alternating. Keep in mind that what we're going to be doing here is radians, not degrees. This is the only time in this class that we will do radians in a sine function, but even then we will be getting rid of the sine function. Now, if you take your calculator and you pull out sine of pi over 6 versus pi over 6. Pi over 6, remember, is 30 degrees. So if we do sine of pi over 6, we're going to get 0.5. This is 0.5. Pi over 6 is 0.5236. They're pretty close together. 0.5 versus 0.5236 is about 5% difference. We will call it error. Because the actual, if we were going to pull the pendulum to the side and analyze it mathematically, the actual would be 0.5. And what we're going to do is we're going to approximate with just this first term. So we're going to look at just this first term here and say if we pulled it to the side by 30 degrees, we would automatically have about 5% error. What if instead we only did 15 degrees, half of that? So sine of pi over 12 versus pi over 12. Pulling out your calculator, this is 0.2588, and this is 0.2618. And now, that's 1% error that we have built into our approximation. What this is saying to, what this whole Taylor series is saying to us is that as long as we keep the angle small, remember we're in radians, not degrees here, as long as we keep the angle small, we're allowed to do this. As soon as you get too far away from 0 degrees, you are not allowed to make this approximation. This is known as the small angle approximation. Small angle approximation. And it allows us to make the equation that we're looking at a lot more user-friendly. So let's go back to that equation and take a look at it. So we've gotten rid of the sine theta. We've gotten our variable out of the sine function, but we still have to deal with this alpha here. We still have two different variables. Now, this looks a lot like simple harmonic motion because what we have is position, this is angular position, and over here we have angular acceleration. And remember the relationship between angular position, between position and acceleration. Acceleration is the second derivative of position, and we have that derived in simple harmonic motion kinematics. Now, if we take a look at the kinematic relationships that we did before, we have position, take the first derivative of position, we get velocity. Take the first derivative of velocity, which is also the second derivative of position, and we will get the acceleration. And we can substitute, you notice that we get back the equation for the original position that we started with. So acceleration is a negative constant times position. That's for linear motion of a mass on a spring. But what if we have a pendulum here that's going in an arc of a circle? Then we have to change what we're doing to account for the fact that it's moving in the arc of a circle. Now, since we don't have a mass on a spring that's oscillating along a straight line path, what we have is a pendulum that's carving out part of a circle. That amplitude A we turn into the radius of the circle, and we divide over, because what we want is not the linear distance, but what we want is the angular distance. So when we divide everything by the radius, what we get is what is the angular position at any given time, given that we started with an angular displacement at the beginning. A equals radius divide by the radius. And our linear position equation turns into an angular position equation where we have theta as a function of time, starting with a maximum displacement that then oscillates through time in the cosine function according to how we decided to start out with, by holding it at its displacement and then letting go at the same time that I start my stopwatch. The derivative works exactly the same way. So when we take the derivative, omega equals d theta dt. And what's going to be confusing here is that we have two different omegas. The one omega that's inside the cosine is the angular frequency that has to do with how fast is the thing oscillating back and forth. And the other omega that is the derivative of theta is how fast is the pendulum bob swinging at this instant. They are two different omegas. Unfortunately, we're using the same symbol in two different ways in the same function. So I'm going to make one big on the other guy, keep the other guy small. So this guy, omega is a function of time, is going to be minus little omega theta max sine omega t. So that big omega is the angular speed of the pendulum bob while it's swinging. And the little omega is the angular frequency of the bob in its motion. This is a number and is a constant. This guy is always changing. And then we can take the derivative of that to get the angular acceleration, just like we did with the linear version. And we end up with exactly the same relationship between angular acceleration and angular position as what we had with the linear acceleration and the linear position. So let's go make that substitution back into our function that we are analyzing. This guy is going to be replaced by minus omega squared theta. And what we've done is we've gotten rid of both the trig function by making a small angle approximation and the second variable by using the relationship, the simple harmonic motion relationship between position and acceleration. And now this equation becomes a lot prettier, or it will in a moment once I cancel things out and rewrite them. And you should notice that what we have on the left and the right is we have a theta on both the left and the right, so that's going to cancel out. We have a minus sign, that's going to cancel out. We have a mass, that's going to cancel out. And we have a length here and two lengths there, so we can cancel one of them. Let's clean this up. On the left, we're going to have G, and on the right, we're going to have an L and an omega squared. Remember, as we discussed before, in our definitions of simple harmonic terms, omega squared, the angular frequency, is related to period. And what I said at the beginning of the video is that I want to end up with an equation for the period of motion of the simple pendulum as it swings back and forth. all of our analysis in simple harmonic motion is let's look for an equation that we can use to analyze the motion for things we measure with a meter stick and a stopwatch. And this guy is going to be 2 pi over t, and we have to square everything. But then at the end, we're going to take the square root. So substituting those guys in and taking the square root, the t, which is on the bottom, is going to multiply up to the top, and then we're going to divide by the L. And then we're going to divide the L by the G. And we end up here with the equation of motion of a simple pendulum, in which you notice it depends on not the mass of the bob. The mass of the bob has disappeared. It's canceled out way back over here. What matters is how long is it and what planet are we on. So if you take this pendulum bob and you make the length shorter, the period should get shorter, and you should be able to see that it swings faster. Let's try that out. We have our simple pendulum still set up to be 1 meter long, and if I pull it to the side and let it go, you can see that it swings back and forth with that rhythm. And you can time it, and it will have a period of between 1 and 2 seconds. Now let's make it shorter and see what happens to the rhythm of the swing. I've now made it shorter by about 40 centimeters. And let's make it swing again and see what happens to the rhythm of the swing. Now if you time it, you should notice that the period has decreased as it goes over and back again. It's swinging faster. I didn't pull it back any farther. It's not swinging through more angle, and it's not swinging through less angle. It's swinging through roughly the same angle, but the swing is faster. If I make it shorter again, the swing will continue to get faster. Now it's short enough that you can see the pivot at the top of the screen, and when I let it swing, it is now swinging much faster. What I can't do is take it to a different planet and show you the swing on a different planet. We'll need some astronauts for that. So the equation for the motion of a simple pendulum, T equals 2 pi root L over G, as we've derived. What you need to be able to do is not just use it to plug in numbers, but also to rederive it starting from torque equals I alpha, and then employing the small angle approximation in the Taylor series, as well as the simple harmonic motion equations for angular displacement in the kinematics as shown, to arrive at this equation. In the next video, since this is now 29 minutes long, we will go back and look at the physical pendulum equation.